Welcome all of you. In the last class, we started analyzing the NMR spectrum. We took simple example of a hypothetical molecule. I showed you how we can generate a spectrum using the family tree approach, and then we took a molecule CH2D2. We simulated the spectrum for different nuclei. I just showed you how in a simple molecule spectrum of different nuclei can be different, appear different, and how do you extract the coupling information, everything is a different thing. Looking at the, if you have the idea of there, I had the idea of the coupling, and using that idea I simulated the spectrum pattern, because I know what are the functional groups present there, carbon coupled to H2, D2, etc. And then we simulated the deuterium spectrum, carbon, proton, everything. We took the realistic examples and showed few examples how we can analyze the proton spectrum, fairly simple molecule, just by using the knowledge of chemical shift, intensity of the peaks, and little bit of using the idea of our chemistry where it should come, like idea of shielding and de-shielding, etc. And of course, using the multiplicity pattern and the using chemical shift, with simple molecules can be straight away analyzed. They are called first order analysis spectrum, which are analyzable in the first order way. They are called weakly coupled. Most of the time, unless you are very much interested in getting the intensities and you have to go into the quantum mechanical analysis of strongly coupled, generally for characterization purposes, which most of the chemists use, this way of analysis will suffice. We will continue further and see how we can analyze few more spectra of several molecules are there, how we go ahead and analyze it. I will take lot more examples today, not only just proton spectrum. Now so far I am analyzing only proton spectrum. There could be heteronuclear coupling, there could be symmetry, varieties of possibilities we can think of. Each of these case 1 or 2 examples I will take and show you how we can analyze this. We go to the next molecule. This is the next molecule which I am showing here. Here how we can go ahead and analyzing. Of course, this phenyl group is a different way, that always comes at 7 to 8 ppm. How to analyze the spectrum of a phenyl group when the molecule contains a benzene ring or a phenyl group, I will tell you that later. But right now you understood what I have written. This is proton 1, proton 2 and proton 3. Why I wrote this as proton 3, why I wrote this proton 1 and 1? First of all from the intensity pattern and then multiplicity pattern. How the multiplicity pattern I arrived at for this phenyl ring, just in this class itself, maybe after a couple of slides you will understand. So don't worry about the phenyl part, I have written 1, 3 and 2, I have made the analysis already. We will assign the other part. Of course, other part fairly simple. First one is CH3. Always start with the rightmost CH3, or the leftmost phenyl group, or OH or NH, something would be there, and very easily you can assign this. What is the next one? This CH3 can couple to CH2, and then this CH2 will become a quartet, but that is not the end of it. It may be having a geminal coupling with this, or coupling with this, or it can have a coupling with this. We do not know. The pattern would be entirely different, very complex. And if you come to this one, I can fairly interpret it in a simpler possible way, because CH2 is attached to oxygen, it comes downfield, and that is the only proton which can have which can appear like a triplet apart from CH3. Look at it, this is coupled only to this, and there is a breakage here, because these phenyl groups are not coupled to this, far away. So obviously there must be one more triplet. This is proton 6, because there is only triplet. Then the problem comes, these 4 different types of protons 1, 2, 3, 4 are here, and they have a funny pattern. How do you interpret that? So this is what we have to understand, and then these are all assumptions I am going to make to analyze. If you want to really assign this one, we have to resort to 2-dimensional techniques, and I would say this is proton 10. Why? Just my assumption is this is the high field, because it attaches to CH3, it comes here, becomes a quartet, and then each layer of the quartet is split because of these 2 protons, and some multiplicity pattern is there. I call it a quintet or a pentet, whatever you are getting it, and I will call this as proton 7. Why proton 7? This is going to be a triplet, this because of this, and each layer of the triplet is becoming a doublet because of geminal or trans coupling with this. So it will be doublet of triplet, which overlaps I showed you earlier, could be a quartet. This could be my assumption. This I would safely say this is proton 7. Of course, still there is a difficulty, we will understand later. This is proton 6, I will say. I already told you this is the only proton which can become a triplet because of this, nothing else. And then this one, this is proton 8. Proton 8 is fairly complex because it has a geminal coupling with CH2 is a triplet, it is a trans coupling with CH3 is a quartet, and it is going to be having a cis coupling with this proton, it is going to be a very complex pattern. And thus complex pattern not only for this is also true for this proton, other proton also. See this complexity pattern you can get for both 8 and 9, similar pattern because both of them have a similar environment almost, except CH3 for this and CH2. This proton experiences CH3 and CH2, 2 CH2s and CH. This also experiences 2 CH2s on H like this. So pattern is almost similar. So there are only 2 such groups like that, 7 and 8. That has to be, I am sorry, 8 and 9. That has to be 8 and 9. We do that. We make a rough guess. Which is 9 and which is 8, I still do not know. It is only a guess I am making. I will show that when you go to 2D experiment, 2-dimensional COSY, I will show you how we can clearly pinpoint and say this is proton 8 and this is proton 9. Right now, only on the basis of the spectral complexity and the coupling because of the neighboring groups, I made this assignment. By and large, it is okay, except there is a confusion between these two. Most of these things I know I am correct. There cannot be anything wrong. Okay, we will go further. This is the molecule, very interesting molecule. There is no phenyl group here. When there is no phenyl group and only aliphatic groups like this, complexity is much better and very easy to, very difficult to analyze, extract information, but easy to make the assignment of protons. But if you want to analyze and get the J coupling, it is not easy. It takes a lot of time. More involvement is required. One thing you can again say this is CH3, no doubt about it. And then next is CH3 coupled to, this is coupled to CH3 becomes a quartet, and then each of them will become a doublet of quartet because of this. And these two protons, as always I said in the previous slide, is very complex. This can have a couple trans coupling with geminal coupling with this, cis coupling with this, same here cis coupling with this, geminal and trans coupling with CH2. So these two protons 6 and 7 are fairly complex. So this has to be here, that I can say. Of course, very easily you can go ahead and analyze most of the things. If you consider this CH4 proton, maybe it can have only maximum coupling with this one, nothing else. What else where else it can be coupled? There is no other way it can couple to any other proton. So obviously this doublet I would say is a CH4. If you consider this proton coupled to this, it is going to be a trans coupling of a doublet, plus it is also coupled to the CH4, it is also possible. So it is fairly a complex pattern. So it starts becoming bit and bit messier and messier. How do you understand this thing? Is a fairly difficult thing. We have to resort to little bit of advanced technology, advanced technique called 2-dimensional NMR for this. But right now I will make a rough guess of the analysis and we will confirm it later. Based only on the multiplicity pattern I will start making assignment. This is proton 9, this is proton 8, true, because it is a complex pattern, and this I would say proton 5. Why I would say this is a proton 5? This can couple to this, become a triplet, and each line of the triplet is further split because of the trans coupling with this and then geminal coupling with this. Similarly, this is a proton 4. This proton 4 can only become a triplet because of this and a doublet because of this. Each line of the triplet will be a doublet. So I would say that. And this is proton 6. Obviously, I told you it is complex. Similarly, this is 7, even that is also complex. Then what is left with you? What is left is this protons, this CH proton. This CH proton is proton 3 can experience coupling with this, can experience coupling with this and experience coupling with this. That is very interesting. When it is experience coupling with trans coupling with this, it will be a doublet, and it is also having coupling with this, it is going to be a doublet of doublet, and each line of the doublet of doublet becomes a triplet because of that. Where can you get that pattern? It is here, doublet of doublet, and each line of that is a triplet. Obviously that is proton 3. Now next is this one, proton 2. This proton 2 is very easy to understand. First of all, it is going to be a doublet, trans coupling with that, and doublet of doublet because of this, and a long range coupling with this. let us see, that is proton 2, and this CHO as a coupling only with one of them. So, it is a doublet. That is how we can make the assignment. That is a very simple assignment. We will go to the next complex molecule, bit complex, appears simple but complex. How do you do that? This is a simple molecule isobutyl propionate in chloroform. Interestingly, you have to see there are two groups of protons here. One, this is one coupled spin system, this is another coupled spin system. In between there is a C double bond O. As a consequence, there is no interaction between this group and this group, they are separated, very well separated. Now we have proton 1, 2 and 3. 1, 2, these two are methyl groups. This methyl group is coming to the high field, but you look at it carefully, this is expanded here, this is a doublet. Why it is a doublet? You should understand these two are equivalent protons, methyl both are equivalent, coming at the same chemical shift, and because of splitting with this one it becomes a doublet. This methyl is a doublet because of coupling with this. Then what is the next one? This proton 2 has coupling with these 6 protons like this, and coupling with this one, very complex pattern. So, very easily you can understand that. What about proton 3? Proton 3 is a very simple thing. The proton 3, because this is only a CH, this is C only single H, whereas this is CH2. So, this is going to be a doublet because of coupling with CH proton. So, this is a doublet, this is proton 3. So, we have very clearly understood this is a doublet, this is a quintet because coupling with 6 methyl protons, and then it is also coupled with the CH proton. This will be a doublet, this will be a more complex pattern because of that. And coming to this 4 and 5, 5 is a methyl group which is this has to be a triplet because of CH2, and this CH2 has to be a quartet because of this CH3. Where do you see that one CH triplet and quartet? This is a triplet and this is a quartet. Obviously, this is the terminal CH3, this has to be CH2. So, very easily we could assign this. There is no difficulty at all. This is a simple molecule. A same molecule we extended further. But here interesting thing you should observe in a molecule like this, look for the chemically inequivalent groups. There are only 4 chemically inequivalent groups because there is symmetry for the molecule along this axis. There is a mirror symmetry. So, we have one CH3, CH2, CH2 and CH2. This is easy 1 and 2 because quartet and a triplet, very easily you can assign this one. What about this one? That is also easy, that is a triplet, that also can be assigned. The problem comes only for this proton. What pattern we expect for this proton? For this proton, what is the pattern we expect? For this for proton 4. Remember, this proton 4 experiences coupling with this CH2 and this CH2. As a consequence, it will be triplet of triplet. You can see that one, complexity is here. This is the next complex molecule group. Obviously, this is proton 4. See, there is a symmetry, up to this is fine, but this, although there is a symmetry, this can experience coupling between this and this. It can experience coupling with 3 and also with this group. That is the pattern you are going to get for this, and we make the assignment. This is proton 1, 4, 2 and 3, simple molecule. We will go to isobutyl butyrate, another different molecule. Earlier as a propionate. Up to this is clearly known, we already understood that. This is going to be a doublet CH3 because of coupling with this. This CH proton is very complex because of coupling with this one and this CH2, and this is going to be a doublet, this CH2, that is also known here. This up to this we knew in the previous molecule. Here now you have to understand. Here we have done only extended this one. Of course, this is CH3 group, terminal group, has to be CH triplet because of this, and this has to be quartet because of this, and each line of the quartet split because of this into a triplet. It is a very complex quintet or sextet pattern, whereas this one is only a triplet. So, with this idea, now we can make the assignment. First, this is very easily you can start assigning. This is proton 1, understandable, it is a doublet because of coupling with 2. proton 2, this is coupled with 3 methyls and this one, then it has to be more complex pattern. Proton 3, it is coupled to this one, only a doublet, 2 CH3 is far away, there is no coupling, fine. And this is proton 4, it has to be a triplet because of this, and proton 5 is a more complex pattern because of 2 CH2s like this, as it could be a sextet. And what about the other one is proton 5, very easily you know that one. Proton 6 is known, is a triplet, proton 5 is known, proton 4, all the peaks have been assigned, simple molecule. But why I am taking this example to show is, when we have to see one proton sitting between 2 other protons, how do you assign the peak? That is what you should look at the multiplicity pattern and then start assigning. This is a fairly easy molecule, but let us see how you can assign this one. First of all, if you look at this molecule, there is one terminal group CH3. This has no coupling with any other proton because other protons are far away. Obviously, it has to be a singlet with intensity more. Where do you see that singlet? This is here. I can safely say this is a CH3 group. Next is 3 different protons, all are different. Here you have to use your idea of cis and trans coupling. Remember when I was explaining the corpus curve, I did explain and I did say trans coupling in such type of molecules are larger than cis coupling, and cis coupling is larger than geminal coupling. This is the order I explained to you. First geminal coupling weak, more than that is cis, more than that is trans. Now look at this, if you want to analyze this, you have to consider this one. This proton experiences one trans coupling, large coupling, and one cis coupling, that is fine. Look at this proton, this experiences one cis coupling 3 bond, vicinal coupling, okay, and one geminal coupling. Whereas this proton experiences one trans coupling and one geminal coupling. They are all of different strengths. So looking at the pattern, multiplicity pattern, looking at the separation of the peaks, you can assign which is which here, very simple. Okay. What we will do is, this CH3 is, I would say this is a CH2 group, this has been expanded here, this is CH. Okay. This C3 experiences this proton 3 a trans coupling which is larger, which is of the order of 14 nets, and then a cis coupling. That is why it is 2 doublets well separated. Next one, this proton 1, it is a large coupling trans well separated, and then each of them is split into a small coupling because of geminal, which is only 1.5 hertz. Continue further, this has to be a proton 2 because this has a vicinal coupling smaller than trans coupling of the order of only 6.6 hertz, and each of them is split into a doublet because of geminal coupling of 1.5 hertz. Very easily you can interpret. Here we use the idea of cis trans coupling strengths. Okay. Remember, in such type of molecules, when you have ethylenic like these molecules, you have to use the knowledge of trans coupling, which is larger than cis coupling, and cis coupling is larger than geminal coupling. Based on that splitting pattern, you can start interpreting. Okay. We will go for this molecule. Similar molecule, but instead of proton here, we have replaced this with a methyl group. This will be identical way of explanation. This CH3 proton is already known, this is CH3, this is proton 1, no splitting, nothing, very well strong singlet, it is there, easily I can do that. Then what remaining? Exactly like the previous example, you have to consider all the 3 are, you have to consider the trans coupling, cis coupling and geminal coupling for each of them. 1 is done, now 2, 3, 4 will assign. I would say this is proton 3. Why did I say proton 3? Logic is simple. This proton can couple to this proton and become a doublet, and this can also couple to this vicinal coupling, become doublet of doublet. So, this large separation is vicinal coupling, and each of the doublet is a other doublet because of geminal coupling, and it cannot have any other pattern. Whereas other two groups, you see, there is a quartet like pattern, that means it is coupled to CH3. When we are looking at CH3, it is coupled only to single protons. Obviously, very authentically I can say this is proton 3, there is no doubt about it. Okay. Now we go further, I would say this is proton 4. Why I would say proton 4? This is a trans coupling very large, and then each lane of this large doublet is split into a quartet because of this vicinal coupling. Cis coupling is there. And go to this one, this proton 2, this is a trans coupling and also geminal coupling here. Okay, very easily looking at, then each of them will be a doublet, and further each length doublet is split into quartet because of coupling with CH3. Okay, this is how we can analyze. We will go further, more complexity. As you go higher and higher, we see complexity keeps increasing. A molecule like this, very easily you can do that. This is CH3, that is a first assumption, there cannot be anything wrong. Proton 1, it will be a triplet. Go to next one, CHO, very easily it comes to downfield because of attached to oxygen, and that will be split into doublet because of CH. You can see it, this CHO is a doublet. Okay. See, this is CH3, this is CHO is doublet of the order of 8.1 Hertz coupling between this and this, CH and CHO. And go to proton 3, this I will say proton 3. Why? This proton 3 is a doublet of triplet. Very easy, because he is doublet because of this, and each of the doublet is a triplet because of this. So that is proton 3. What about this one? This a complex pattern is there. This can experience coupling with this, and also there is a long range coupling with this. So that must be proton 4, we can interpret that one and go further. So like this, more or less all of them have been interpreted, all the peaks have been entered. So I will go back again, and you can see carefully. I have removed all the marking. This is CH3 singlet, a triplet. This is CHO is a doublet because of CH coupling, and this is a proton 3. It is this proton 3 has a coupling because is a doublet is expanded here. It is doublet of triplet, and this is proton 2. This is having quartet of doublet because it is a quartet because of this, doublet because of this, and also has a long range coupling with this. And this 4 is having doublet of triplets because it is a doublet because of this, doublet because of this, and also long range coupling to this, and that is how we understood this one. Okay, this is all so far we were discussing about the analysis of the proton spectra of molecules containing only aliphatic protons. So far we did not bring in the phenyl group, only one example was there, but I said I will explain it later. How do you analyze the spectrum of molecules containing phenyl groups? That is what we should understand today. Before going further, please always remember, if I have aromatic protons, especially benzene rings, this is the order of coupling we should remember. Ortho coupling in benzene is between 7.5 to 8.5 Hertz. It could be anywhere around that. Meta coupling is 1 to 2 Hertz. Para coupling can go from 0.3 to 1. Even sometimes 1.5. That is okay. Approximately we can say less than 1 Hertz we can say. This is a 5 bond coupling para, 4 bond meta, 3 bond ortho coupling. This is information is needed for us if you want to analyze the proton spectrum of aromatic systems. How do we get the splitting pattern in different phenyl groups? The phenyl groups can have substitution, it can be monosubstitution, symmetrically disubstituted, asymmetrically disubstituted, symmetrically trisubstituted, asymmetrically trisubstituted. In each of these cases, the spectrum would be different. The way you see the spectrum will be different. Then we can use this knowledge to analyze the spectrum of such molecules. We will start with a monosubstituted benzene. This is a simple molecule. There is a perfect symmetry along this axis. This and this are identical. These two are orthoprotons are same. Then these two orthoprotons, when I look at it in this molecule, this is going to be doublet of a doublet. Why it is a doublet of a doublet? Because these two are identical single proton, but each of them is split by orthocoupling into a doublet. See, it will be split into a doublet like this, and each line of this doublet is split by a para coupling of the order of 0.5 Hz. That is why it is a doublet of doublet. Larger separation correspond to orthocoupling, smaller separation correspond to metacoupling. I am sorry, metacoupling with this, correct, metacoupling for these two orthoprotons. So, if I have a monosubstituted benzene, if you get a pattern like this large doublet and each line of these is a doublet of doublet, fairly you can assume they are ortho to the substituent. Next we will go further. This is the orthoproton. What is the next one we can think of? This is ortho, this is it is called doublets of doublet. We will go to paraproton. What is the pattern we expect for a paraproton? Very simple. Both this thing will split this into a triplet. Before that, of course, there are two orthocouplings, large couplings. These orthocoupling will split this into a triplet, and each line of the triplet further split into another triplet because of two equivalent metaprotons, and this is how the pattern you get. And this large separation correspond to this coupling, these two coupling, orthocoupling, and you get this to the here it has to be orthocoupling has to be identical because it is a monosubstituted benzene. There is a symmetry axis. As a consequence, this coupling and this coupling are identical. When the couplings are identical, we also discussed you will get a triplet 1 to 1 because two lines of the center overlap, and you get a triplet, and each line of the triplet has a metacoupling like this, become triplet of triplets. And if you have a paraproton in a monosubstituted benzene, you get a pattern like this, triplet of triplet. So, easily you can identify that and make the assignment. Okay. What about this is called triplets of triplet. What about the other one now, metaprotons? This is fairly difficult. Here we can think of when the two orthocouplings are identical. Okay. When the two orthocouplings could be different or identical, but we have to say in this case because of the symmetry they are not different. We of course only for this one we do not know whether this coupling should be same because of the symmetry, in which case if they are different normally they will not be different. If they are different, this will be doublet of a doublet because large coupling is one orthocoupling and other one is other orthocoupling. Usually because there is a symmetry they are same, in which case if both are identical, again this paraproton is going to be a doublet. This possibility is very low, you will not see unless there is a distortion in the molecule. Normally there is no distortion because of substitution, there is a symmetry, C to symmetry along this axis. As a consequence, this proton will have orthocoupling with this and metacoupling with this. So, it has to be only triplet. Okay. And metacoupling if it is there, of course it could be, I am sorry I am thinking of not this one, I am looking at this one. This has one coupling with this and one coupling with this, it is a triplet. We look at asymmetrically ortho disubstituted benzenes, it is a monosubstitute we took. Now let us take the example of asymmetrically ortho disubstituted. What will happen? Asymmetrically means these two substituents are different, x and y. Then what is the pattern we expect? Is there any symmetry for this molecule? No symmetry at all. All these 4 protons are chemically inequivalent. A is different, B is different, C is different and D is different. Let us see how do you get the proton chemical sheet of proton A. How the multiplicity pattern you get. Proton A can experience orthocoupling with this, can experience metacoupling with this and also experience paracoupling. So, what is the pattern you expect? You expect first orthocoupling and each of the doublet is going to be doublet of doublet because of metacoupling, and each of them is going to be doublet of doublet of doublet because of paracoupling, and this is the pattern you are going to get. You see the point? This is what you are going to get. If you have asymmetrically di-substituted benzenes, if I look at one of these protons, you are going to get 8-line pattern, and from the pattern you can understand from the center is a chemical shape. This is one ortho coupling, this is meta coupling, this is para coupling, all are different. Same way if you look at the proton B, what will happen in this molecule? Proton B, if you look at this molecule, proton B experiences one ortho coupling and one meta coupling. This can give rise to again 8-line pattern, because 2 ortho coupling and 1 meta coupling, assuming that meta couplings are different. It can happen it can happen this coupling and this. For example, I am looking at proton B, it can have one ortho coupling, one meta coupling. If two ortho, not meta coupling, if two ortho couplings are different, you get like this, and you will have a pattern like this, DDD. If two meta couplings are identical, if you look at the proton B here, I should write in the molecular structure there. If you look at the proton B here, it can have two ortho couplings and meta coupling. Not if the two ortho couplings, this is not right, meta, this is ortho. If two ortho couplings are identical, again it is ortho, then you will get triplet of doublets. Two ortho couplings are triplets, identical, if they are identical, and each one of the triplet is going to be a doublet because of meta coupling. So, two ortho couplings are identical with this is the pattern triplet, and then because of meta coupling it will be doublet of triplets. This is how it is. This is how it is, we are going to get. It is a triplet of doublet. What about the proton C? Again same, here I have written correctly. If J ortho are equal, it is going to be doublets of triplet. If the J orthos are not different, are identical, then it is going to be DDD, similar to HB. Okay. Here also if you see this one, it can have this and this ortho coupling. If they are identical, it will be a triplet, and because of the meta coupling, it is going to be a doublet of triplets. If they are all different, it is going to be DDD, 8-line pattern. Go to this last one, proton. Last one is proton D. Is this one is exactly has the pattern similar to A, because it is one ortho coupling, one meta coupling, one para coupling. It will be 8-line pattern. This is how you will get the spectrum if you have asymmetrically ortho disubstituted benzene. So, simply remember, if you have asymmetric ortho substituted, the protons which are close to the ortho to the substituents can have DDD, 8-line pattern. Protons which are meta to the substituents can be a doublet of triplet or 8-line pattern, depending upon whether the ortho couplings are identical or different. So, this is how you have to start analyzing the proton spectra of phenyl ring. Lot more examples are there about what happens if you have meta substitution, symmetrical or asymmetrically, how does the pattern come. We will explain that and then take the real example of this thing, and we will start discussing that in the next class. So, today I took the example of analysis of the many protons, example of many molecules. We analyze the proton spectra simple. They are all weakly coupled, first order analysis is possible. We are looking at the neighboring group, looking at the multiplicity pattern, looking at the chemical shape, looking at the intensity pattern. We were able to assign lot of peaks, very easily we can do that. For olefins or like ethylenic molecules with a double bond, we understood depending upon the trans coupling, cis coupling and geminal coupling strengths, we could easily assign which is which. That was not difficult at all. So, we took the example of many such molecules. One molecule can have two coupling, two bond, coupled with two protons, three protons or groups of protons. Multiplicity pattern becomes very complex. Looking at the complexity of the multiplicity pattern, we could make rough estimate of many of the rough assignment of all the things. By and large they are correct, but how do you authentically say that? We have to go to the higher advanced NMR techniques. Further we went to the phenyl groups. We also said in the phenyl group, mono substituted, how do we get? If it is asymmetrically ortho substituted, how we get? We understood the spectrum. So, we can go further and see what will happen to different substituents from the next class, and then we analyze more complex spectrum with heteronuclear couplings, satellite spectra, varieties of things, subspectral analysis we can do. We will continue that further. So, I will stop here. Thank you very much.